Hello everyone, welcome back to Android with Arya. And on this channel, our goal is not to just learn Android development, but to understand how Android works under the hood. So in the previous video, we started building our Jetpack Compose project by creating navigation raw. The idea behind this playlist is to build real-world applications while learning different Compose concepts along the way. However, after that video, many of you shared an important suggestion. You wanted to understand the fundamentals before diving deeper into Jetpack Compose. The questions like why was Jetpack Compose created, what problems did it solve, and if traditional XML view system was already working, why did Google introduce an entirely new UI toolkit? I thought those questions were great questions because learning an API tells you how to use a framework, but understanding the architecture behind it tells you why it exists. And once you understand the why, learning the how becomes much easier. So in this video, we're not going to write any compose code. Instead, we're going to take a deep dive into Android framework itself. We'll understand the traditional XML view system renders the UI, how the view hierarchy works, what happens during the measure, layout, draw pipeline, why developers had to manually synchronize data with the UI, where the imperative approach starts to become difficult as application grows, and finally, how Jetpack Compose solves many of these architectural challenges with a declarative state-driven approach. By the end of this video, you won't just know what Jetpack Compose is, you'll understand why Google built it and why it's one of the best architectural shifts in the Android development. So without wasting any more time, let's dive in. So before we begin, let's take a quick look at what we're going to cover in this video. We'll start by understanding the fundamental difference between imperative and declarative UI, because that's where the entire journey begins. Next, we'll deep dive into Android view hierarchy and see what actually happens behind the scenes when an XML layout is inflated into real view objects. From there, we will explore the measure, layout, and draw pipelines to understand how Android renders every pixel on your screen and how methods like invalidate and request layout fit into this process. After that, we'll discuss one of the biggest architectural limitations of the traditional view system, the state disconnect, and understand why keeping the UI synchronized and application data became increasingly difficult as application grew. Once we understood the problem, we will move on to the state as a single source of truth and see how Jetpack Compose changes the relationship between the data and the UI. Finally, we'll bring everything together by understanding the declarative paradigm shift and why Jetpack Compose represents a fundamental change in the way Android UIs are built. So by the end of this video, you will have a clear understanding of how the traditional view system works internally and where its limitations come from, and why Google introduced Jetpack Compose as the modern approach to Android UI development. So let's get started. So section 1, imperative versus declarative UI. Now that we have a roadmap of what we're going to cover, let's begin with the most fundamental concept behind Jetpack Compose, the difference between imperative and declarative UI. If you have been building Android applications using traditional XML view system, you have already been working with imperative programming model. But what does imperative actually mean? Let's understand it with a simple real-world analogy. Imagine you have hired a painter to renovate your living room. To get the result you want, you have to give the painter step-by-step instructions. Like what? We can say this, paint this wall blue. Now paint the door color white, move the chair to left, hang the painting on that wall, something like that. So every individual action depends on your instructions. If you forgot even one step, the final results won't look the way as you expected. The traditional Android view system works in the exactly same way. So as a developer, we manually tell Android what needs to change, We update a text view, hide a progress bar, show the button, change the background color, or replace an image. Every UI update in our is a developer's responsibility. Now let's compare that with the declarative approach used by Jetpack Compose. Instead of hiring a painter, imagine hiring an interior designer. So now you don't have to explain every brush stroke or every furniture movement. Instead, you will simply describe the final result, that I want a modern living room with blue walls, minimal furniture, and a clean design. The interior designer have a responsibility to decide how to achieve that outcome. Jetpack Compose follows the same philosophy. Instead of telling the framework how to update the UI step by step, we simply describes what the UI should look like for the current state of our application. Compose determines which part of UI need to be updated and perform these updates automatically. So it's all dependent on the state of our application. At the first glance, this may sound like a small change in a programming style, but as we will see throughout this video, this single architecture shift solves many of the challenges that developer faced with the traditional Android view system. So section 2, understanding the view hierarchy. Now that we understand the difference between the imperative and declarative approaches, let's take a look at what actually happens behind the scenes when Android loads an XML layout. So when we call set content view, in that we find that we initially pass that r.layout.activity_main. It might seem like Android magically displays the UI on the screen, but in the reality, a lot of work happens before the first pixel is ever drawn. The process begins with the component called the LayoutInflater. Its job is to read your XML file and convert every XML tag into an actual view object in memory. Whether it's a text view, button, image view, linear layout, or constraint layout, each tag is initiated as its corresponding Java or Kotlin object. Once all these view objects are created, Android connects them together into an hierarchical tree known as a view hierarchy. At the very top of this hierarchy sits the decor view, which is created by the Android framework as the root of the application window. Inside the decor view, Android places your application's root layout, such as constraint layout, linear layout, or any other root view that you have defined in your XML file. The root view then contains its own child views, which may themselves contain additional child views, forming a complete tree structure representing your entire UI. Now here's something interesting. Every view in this hierarchy is much more than just something displayed on the screen. Each view maintains information about its parent, child views, its size, its position, padding, margin, visibility, background, focus state, touch listeners, and many other properties required for rendering and handling user interactions. In other words, every UI component is a fully fledged object participating in the Android rendering pipeline. The view hierarchy is the foundation of everything that follows, from measuring and laying out views to drawing them to the screen and handling touch events and updating the UI whenever a view's property change. So before we move on, let's clear up a very common misconception about view hierarchy. Many developers believe that every time a view is updated, Android searches the entire view hierarchy again to find that view. Fortunately, that's not how it works. When you call find view by ID, Android traverses the view hierarchy once, only once, to locate the view with a specified ID. Once it finds the view, it returns the direct object reference that points to the view in the memory. From that point onwards, whenever you interact with that view, for example, by changing its text visibility and or background color, Android doesn't perform another hierarchy traversal. All those operations happens directly through the stored object reference, making them fast and efficient. So if we view lookup isn't the real problem, so then what it is? The actual challenge lies elsewhere. The traditional view system requires developer to manually manage the relationship between their application data and the UI. Whenever the underlying data changes, it's the developer's responsibility to identify every affected view and update it explicitly. An application become larger and more complex, keeping the UI synchronized with the application state become increasingly difficult. And that's exactly the problem we will uncover in next few sections. Section 3. Measure, layout and draw. Now that we understand how Android builds the view hierarchy, the next question is, how does that hierarchy actually become the user interface that we see on the screen? This is where Android rendering pipeline comes into the picture. Whenever Android needs to render or re-render the UI, whether it is during the initial screen creation or after a layout change, it goes through three fundamental phases. First is measure, second is layout, and third one is draw. You can think of it like constructing a house. The first step is the measure the phase. Android starts from the decor view and traverses the entire view hierarchy. It asks every view a simple question. How much space do you need? Each view measures itself based on its own content and constraints provided by its parent. For example, a text view calculates the space required to display its text, while a linear layout measures all its child views before determining its own size. Once every view has been measured, Android moves to the second phase, which is layout. Now that every view knows its measured width and height, Android determines where each view should be positioned on the screen. It assigns the coordinates such as left, top, right, bottom, establishing the exact location of every element within the hierarchy. Finally comes the third phase, which is draw phase. At this point, Android provides a canvas and every view draw itself onto it. Backgrounds, text, images, borders, shadows, and every other visual element are rendered in this stage. Only after all three phases, measure, layout, and draw, have completed does the final UI becomes visible on the screen. Understanding this rendering pipeline is essential because in the next section, we will see how methods like invalidate and request layout interact with these phases and why they play such an important role in a traditional view system. Now let's consider a much more simple scenario. Suppose you only want to change the appearance of a view. For example, updating the text color of a text view or changing the background color of a button. In the case like these, the size and position of the view remain exactly the same, only its visual appearance has changed. Since Android doesn't need to measure the view again or calculate a new position, running the entire rendering pipeline would be unnecessary and inefficient. So instead, the view is invalidated. You can think of invalidate as a signal sent to the Android framework saying my layout hasn't changed, but my appearance has. Please redraw me during the next rendering frame. Notice something important here. Invalidate doesn't redraw the view immediately. Instead, it marks the view as dirty and schedules a redraw for the next rendering pass. This allows Android to batch multiple UI updates together instead of redrawing the screen repeatedly. Because only the appearance has changed, Android can skip the expensive measure and layout phases and proceed directly to the draw phase, where the view is simply repainted and its updated appearances. This optimization is the one of the reason the traditional view system is quite efficient when only visual properties changes. So now let's look at different situation. Imagine the text view is using wrap content and instead of a short message, you set a much longer piece of text that wraps it into multiple lines. This time, changing the appearance isn't enough. The view's dimensions have changed, which means the existing layout is no longer valid. In this case, simply invalidating the view won't solve the problem. Instead, the view requests the new layout by calling request layout. You can think of request layout as telling the Android framework, my size may have changed, please recalculate my layout before redrawing me again. The important thing to understand is that when one view changes its size, the impact often extends beyond that single view. Its parent may need to allocate more space, neighboring views may need to shift to new positions, and in some cases, multiple levels of view hierarchy must be recalculated. That's why request layout is significantly more expensive than inbuilt date. It doesn't just repaint a view, it tells Android that the existing layout may longer be correct, and that's a new layout pass is required before the next frame is rendered. So here's an interesting question. What happens if you change multiple properties of a view before the next frame is rendered? For example, imagine you change both the text color and the text content, where the new text is long enough to affect the view's size. So two things we are changing, color and its size. Does the Android perform two separate rendering passes? Fortunately, it doesn't. Instead of processing every request immediately, Android schedules these updates and batches them together before rendering the next display frame. If a layout recalculation is required, Android performs a single rendering pass that includes measuring, laying out, and finally drawing the updated UI. There is no unnecessary duplication of work. This batching mechanism is one of the reasons that the traditional view system performs much better than many people assume. However, notice something very important. Even though Android efficiently batches rendering operations, the responsibility of deciding when the UI should be updated still belongs to the developer. You still need to update the correct view, trigger the appropriate UI changes, and ensure that every part of the user interface stays synchronized with your application data. As applications become larger, this manual coordination, not the rendering pipeline itself, become the real challenge. Section 4, the great state disconnect. Everything we have discussed so far might leave you wondering, the view system seems quite efficient. It avoids unnecessary rendering, batches UI updates, and optimizes the drawing process. So where exactly is the problem? The answer isn't in the rendering pipeline. It's in the relationship between your application's data and the user interface. As Android application evolved from a single screens to large data-driven applications with multiple UI components, a fundamental limitation of imperative approach became increasingly apparent. So let me ask you a simple but very important question. What happens if your application's business data changes but you never tell the UI about the change? The answer is nothing. Your data changes successfully, but the UI continues to display the old information because the traditional view system has no idea that business data has changed. And this is where the real challenge begins. You can understand and think of it like as a disconnect between the state and the UI part. Let's understand this with a simple example. Imagine you have a variable in your application, username, something Arya, okay, and somewhere on the screen a text view is displaying that value. Now suppose your business logic updates the data username to John. At this point, what do you expect to happen? Should the text view automatically update and start displaying John? The answer is clearly no. It continues to display Arya. But why? Because the traditional Android view system doesn't observe your business data. It has no knowledge that the username variable has changed until we say so, or we tells it that the particular text view has changed. From Android's perspective, all that happened was that Kotlin variable was assigned a new value. Nothing informed the text view that it should be updated itself. As the developer, it's your responsibility to manually synchronize the UI with the new data by writing something like textView.text or set text equal to the variable name. Only then the view update and the user finally sees the John on the screen. That is why we mean about the state disconnect. Your application's data and your UI exist as two separate worlds, and it's the developer's responsibility to keep them synchronized manually. So now let's take this one step further. So far, we have looked at simple example with a single text view, but real world Android applications are rarely that simple. Imagine you are building an e-commerce application. Okay, so a user taps the add to cart button. At first glance, it looks like only one piece of data has changed, the number of items in the cart, but in reality, the single state changes affects multiple parts of the user interface. The cart badge should display the updated item count, the total price should be recalculated, the recycler view should show the newly added product, the checkout button might need to be enabled. Perhaps the toolbar also displays the current cart count. So one single action can have multiple updates. So all of these UI components depend on the same underlying business data. However, the traditional view system has no understanding of this relationship. It doesn't know that these views are connected to the cart data. It only knows that how to update individual view properties when the developer explicitly tells it to. As a result, the responsibility of keeping the UI synchronized falls entirely on the developer. If you accidentally forgot to update even one of these UI components, the application enters an inconsistent state. Some part of the interface reflects the latest data while other continue display the stale information. The business data itself is perfectly correct, but the problem is that the UI interface was never informed about the change. As applications become larger and more complex, managing these synchronizations manually becomes increasingly difficult and sometimes feels like it's a boilerplate too. And this is one of the fundamental architectural challenges of the traditional imperative view system. Now it's worth mentioning that Google later introduced solutions such as view model, live data, and data binding to reduce this manual synchronization by allowing the UI to observe data changes. These were significant improvements, but they were still additional layers built on top of the traditional view system rather than a redesign of the UI framework itself. Jetpack Compose takes a fundamental different approach by making state-driven UI the foundation of the framework from the beginning. So you can see the difference, how they both works. Section 5, state as a single source of truth. So how do we solve this problem? As Android application become larger and more complex, it became increasingly clear that manual synchronizing the user interface with the business data wasn't a scalable approach. What we really needed was a fundamental shift in the way we think about building UIs. Instead of asking developer to manually update the UI, whenever the application's data changes, what if the UI could simply become the reflection of that data? This idea is known as the state as the single source of truth. Jetpack Compose is built around this principle. Rather than treating the UI and the application state as two separate worlds that need to be manually synchronized, Compose makes that state of the foundation of the entire UI. Whenever the application state changes, the Compose runtime is notified automatically. It determines which part of the UI is dependent on that state and updates only those portions of interface. As developer, we no longer focus on how to update the UI step by step. Instead, we simply describe what the UI should look like for a given state, and Compose ensures that the interface always stays synchronized with the underlying data. This shift from manual managing UI updates to declaring the UI as a function of the state is one of the biggest architectural challenge introduced by Jetpack Compose. At this point, you might be wondering if developers are no longer responsible or manually updating the UI, then how does the Compose know when the application state changes? That's a really good question. That's the key innovation behind the Jetpack Compose. Unlike the traditional view systems, where the framework only reacts when developer explicitly updates a view, Compose is built around observable state. Whenever the application state changes, the Compose runtime is automatically notified. It identifies which part of the UI dependent on that state and schedules only those parts for recomposition. Think of about this is from about traditional view system. Previously, the workflow looked something like this. Some business data changes, developer updates the view, invalidate or request layout, then after measure, layout and draw phases happens. In Jetpack Compose, the flow becomes, because it's dependent on state. So state changes, Compose runtime detects the changes, recomposition happens, then measure, layout and draw pipeline. Notice that measure, layout and draw haven't disappeared. Compose still relies on Android's rendering pipeline to display the interface on the screen. The real architectural challenge and changes happens before the rendering begins. Instead of developers manually deciding which view needs to be updated, the Compose runtime automatically determines which part of the UI dependent on the change state. Recompose only those of the portions and then hands the updated UI to the rendering pipeline. We'll explore how the Compose runtime detects the changes and how recomposition works internally in the upcoming videos. For now, the important takeaway is this: Compose didn't replace Android's rendering pipeline. It replaced the way UI updates are triggered. Section 6. The declarative paradigm shift. So now let's bring everything together. At the beginning of this video, we asked a simple question. Why did Google create Jetpack Compose when the traditional Android view system was already capable of building modern applications? The answer, as we have seen, has very little to do with Android rendering performance. Android's rendering pipeline measure, layout and draw was already highly optimized, and it continues to exist in the Jetpack Compose today. The real challenge was how the UI state synchronized with the application's data. In the traditional view system, that responsibility belonged entirely to the developer. Every time the application state changed, the developer had to determine which view needed updating and manually keeping the interface consistent. Jetpack Compose fundamentally changes that responsibility. Instead of manually updating individual UI components, we simply describe what the UI should look like for the current state of the application. This is the core idea behind declarative UI, often expressed as UI is a function of a state. In other words, the user interface is simply a representation of current application state. When that state changes, the Compose runtime detects the changes, determines which part of UI dependent on it, performs recomposition when necessary, and then hands the updated results to the Android existing rendering pipeline. As developers, our focus shifts from manually managing UI updates to managing the application's state. That's the real architectural revolution behind Jetpack Compose. It isn't just a new syntax or another UI toolkit. It's a complete different way of thinking about building UIs. But this naturally leads to another question. If Compose automatically knows which parts of the UI needs to be updated, how does it actually track the state, remember previous values, and recompose only the affected UI instead of rebuilding everything? That's exactly what we will explore in the next video. where we will deep dive into the Compose runtime, remember mutable state of, snapshot, and recompositions to understand how Compose works under the hood. I'll see you in the next one.